that it works as well or better than a conventional model trained on an order of magnitude more data. So this model is trained on 2,000 hours, and they're about the same on the Fisher, but the deep neural network is actually still winning on the switchboard data. Okay, and that work is now being launched commercially by Microsoft. Okay, just very quickly, one final dimension that we won't say much about, but it's just interesting to know about, is that there's actually a neat way in which deep learning models fit well with current movements in computational technology. And so here's one example of that. So Senna is a sequence tagger developed by Collider and Western, which performance is basically as good as all other state-of-the-art sequence taggers for parts of speech, NER, tasks like that. But interestingly, it runs an order of magnitude faster and uses way less memory than conventional feature-based CRF taggers of a similar sort. And so there just are these changes in technology that favor deep learning. So in NLP, when we have our typical CRF models, we might have our 10 million features, and that means we have a ton of stuff spread through memory. And then we normally try and make our models fast by exploiting sparsity. So that's things like our parsers have sparse grammars, and we see where the cells are filled with different components and so on. But both of those are things that work really badly with modern machines. Lots of memory accesses, lots of branching, really bad for modern computing technology. So actually, if you can do things with dense vectors, it just can often be much faster. That's true even in the simple case of one machine, but it becomes even more and more true once you move to multi-core CPUs, and even more so if you start doing computing on GPUs. Okay, so I hope that's convinced you that this is something that you should know about, and now we just need to get on to some of the details of how might you do this, rather than thinking that there's a miracle happening inside the box. Okay, so the plan of the tutorial is in the first part, we're going to start giving an easy introduction to how do neural networks work and how can you use them, and looking in particular at the unsupervised pre-training and looking at some of their advantages, how they're trained. In the second part, we're then going to focus on recursive neural networks and work through the theory and applications of those. And then the third part is a bit more of a grab bag, where we'll look at some more applications, discuss some of the tricks for really getting this to work, and have some of the discussion of the big picture issues. Okay. So, like all fields of science, deep learning has some of its own terminology, and you just have to learn a few new words to understand what's going on. It's kind of the same as if you do support vector machines. You just have to start learning to talking about kernels and things like that rather than other words. But something I hope to convince you of today is that for most people in the NLP community who've seen other kinds of discriminative classifiers, that really most of the basics of what's going on in neural networks you already know and understand all of it. It's just you have to learn a few new words as to how things map across to each other. Okay, so where I'm going to start this introduction from, and hope that everyone has some familiarity with, is with a Maxent model, or equivalently a logistic regression model. So this is the classic version of the formula that you normally see in NLP papers for a Maxent classifier. So we're doing a conditional probability of a class given some data items, and then we're making features out of the class and the data items. Each feature has a weight, and then we're putting this through these X and a normalization term to turn into probabilities. Okay, so the first thing to know is something that's just like this is used all the time in neural networks. It gets called a softmax layer. Having a softmax layer just means that you've got some inputs and then you're putting them through this kind of form of normalization of trading off the different ones in the denominator. I mean, normally, rather than being written quite like this, the summation is suppressed as in here, and we're turning this into two vectors, and then we're doing a vector dot product. And that's commonly the top layer of a neural network, such as when you're doing 1 of n classification. But let's just move from that for a moment now and look at how we get from the kind of classic Maxent model form to the standard logistic regression model form that you see in a stats textbook. And the way we do that is starting off from here, that what we're doing is, let's consider just the 2-class case, and so then we can expand out the denominator for the 2 classes C1 and C2. And then we simply just do this trick where we multiply by 1, written in just the right form, so that these 2 terms in the numerator are the opposites of each other, so they cancel out to give 1. And we also then get a 1 for the first term in the denominator. And then for the second term, what we're getting is the difference between the 2 feature values for class 1 and class 2. And if we decide to call that difference in feature values x, then we get into the classic form of a logistic regression model that you'll generally see in statistics. And from there, for what we're going to do for this, just want to make one more teeny move. We can rewrite this formula in 2 parts. We can say that on the inside, we've got this dot product between the feature values and their weights. And then what we're doing that is we're putting it through a function form, which we're here calling f, where particularly here our f is this logistic function, which is doing this mapping of real numbers onto 0, 1. It's useful to separate out those 2 things, the linear algebra part, the dot product, and then the non-linearity that you're pushing it through here, this sigmoid logistic function. So that picture is exactly what a basic neuron computes. So here is our neuron. So it has some inputs and it has an output. And how it's going to calculate its output is it's first of all going to do a dot product between the inputs and the weights the neuron has, the parameter values of that neuron, and then it's going to push the output of that dot product through a nonlinearity, and that will give its output value. So it's doing exactly the same thing. There's one teeny footnote that's mentioned there on the right. I mean, there's always this 2 ways to do it. One way of doing it is that somehow you want to deal with an intercept term, and you can either have one feature that is always on, which is what we most commonly do in Maxent models, and then you just learn a weight, which is the class prior to that feature, or else you can separate it out as a separate intercept term, which then corresponds to this feature of the weight of 1 here. Okay, so now we understand what one neuron is doing, and one neuron is doing precisely neither more or less than running a logistic regression. So what we can then do is take a whole bunch of neurons, and each neuron is going to be running a little logistic regression. But there's one difference, and the difference is that we haven't decided ahead of time what variables these logistic regressions are going to try and predict. That they're going to learn based on some optimization function what they're trying to predict. So actually this model form here is actually exactly the model form of a restricted Boltzmann machine, for what it's worth, and it imposes on top of that a particular function that you're trying to optimize. But we don't have to stop there. Once we've got the outputs of these logistic regressions, we can feed them into another neuron, another logistic regression function. And so what we'll then find is if we have here, say, a supervised target value, so then there is supervision as to what this neuron is going to predict. And that means we can make use of that by projecting backwards so that these neurons will automatically learn good things to predict, to try and predict the eventual output. And we don't have to stop there. We can keep on going, and before we know it, we have a deep network. Okay, so just one more tiny bit of getting people used to the notation that we're going to be using throughout this. So far we did one neuron at a time, and we said that it had this form here of weights, the dot product of weights times the inputs, put stuff through a non-linearity. But that's true for the second neuron and the third neuron. And so if you put those all together, you have in here a matrix of weights. And I've sort of given these as matrix indices. And so we can say that what we're getting on the output, the A variables here, is first of all, we're multiplying the input vector by a weight matrix, and then we're running the Z vector through F, where F is the same nonlinearity applied element-wise. Okay, so that's great. How do we train these W weights? Well, if it's a supervised single-layer neural network, we can just train it exactly the same as we train a max-set model. We calculate the gradients of our model, and we work to optimize our prediction of the outputs. And we can do that by using stochastic gradient descent, or we can do it by any of the other means that people have advanced for optimizing functions with things like max-set models, the conjugate gradient, LBFGS, quasi-Newton methods, things like that. Of course, a simple max-set model is a convex model, and so we know that we can run these algorithms and find the global maximum. That's not true once you go to a deep network. So in a deep network, there'll be normally lots and lots of local maxima. So that's exactly the same that also happens in CRS. So people have built hidden layer CRS for various applications such as Crotonian, Collins, and they have exactly the same problem with local maxima. But what we do about that is just cross our fingers. We're going to use exactly the same techniques of running stochastic gradient descent or other kinds of optimization procedures to improve likelihood, and that then leads into the space of the algorithm of backpropagation algorithms. So one final note on this part, and that's just to say a fraction more about the role of nonlinearities. So when people present max-set models or logistic regression, the way you motivate sticking in the logistic function is saying, well, we've got these features and weights, and that can give us any real number. And what we want to do is we want to map that onto a probability. So we want a function that goes from any real number to 0 to 1, has these sort of nice properties in terms of multiplicative factors of the odds that people talk about. So, that's all true. It's not really so much the motivation for most work in deep learning. The way to think about the nonlinearity in deep learning is it's a way to enable us to do function approximation of very complex functions. So the crucial thing to note is deep networks just don't achieve any extra power unless you put in nonlinearities. So if you build a deep network where all it was doing these dot products at each layer, you'd have nothing more powerful than a single layer that did a dot product. You'd just be able to pile it down into a single linear transform, and you could never build anything that wasn't a linear transform. So it's by putting in these nonlinearities that you can build universal function approximators that can come extremely close to any function that you can define. And on the other hand, most of the time in deep learning, the probabilistic interpretation isn't so important. It is for some models, such as the Boltzmann machines, where they remain probabilistic, but a lot of the time it isn't. And people also use other kinds of nonlinearities quite a bit. So in particular, you'll see mention of hyperbolic tan being used quite a bit later. Okay, so what I hope to have convinced you on this is that, basically a lot of the basics of the math. It's just you remember they're called different things. So we're now going to call our logistic regression a neuron. We're going to have activation levels instead of response variables. Backpropagation is really just running stochastic gradient, and when later on if you come across weight decay, that really just means doing regularization of your models. Okay, so that's the basics of what the learning of neural network models looks like. But I just want to come back again to the motivation that was mentioned early on, which was this idea that before, in the old days, deep learning models didn't really used to work. And so this is showing this is actually for OCR data. And so this is a classic purely supervised neural network. And what you see is it improves fractionally. These are error rates, classification error rate, going from having one hidden layer. As soon as you have more than one hidden layer, the performance starts to get a lot worse, not better. And compared to that, the crucial big advance that happened was then the development of these unsupervised pre-training methods. And so on the right-hand side, then there are results for the same kind of model that after applying unsupervised pre-training. And what we discover is that, well, first of all, just all of the error rates are enormously lowered. But secondly, you then have much more effective deep learning. So the model's performance is increasing down to having a 4-layer net. And it's only once you get to the 5th layer that performance starts to get worse again. So now I'm going to move into looking at word representations and how to learn these unsupervised representations that give us a lot of the power. Okay, so the crucial thing to notice is that the vast majority of work in statistical NLP isn't any different to the corresponding work in rule-based NLP in regarding words as atomic symbols. And so if you think about that in vector space terms, what that means is our representation is a vector with a 1 in one position and a 0 in every other position. And this vector is enormously long. You know, it might be 50,000 long from entry bank vocabulary. It's about 13 million long if you use Google Web Corpus. So this gets referred to in neural network land as a one-hot representation. And so it has this enormous problem, is that it gives you no representation of similarity and ability to generalize. So if we ask about what's the relationship between motel and hotel, there's no relationship, that they're just orthogonal to each other. So compared to that, that's where there's then been a lot of work on distributional similarity representations. And what people have found is you can get an enormous amount of value from representing word by means of the context in which it appears. And that makes things a lot better in this classic Firthian way of you shall know a word by the company it keeps. And the best known and most used methods in NLP for doing that are these hard clustering methods, so Brown clustering, Nye's exchange clustering, and these work really, really well. They do a great desparsification, and they're a great example of unsupervised pre-training. But nevertheless, as motivated at the beginning, we're interested in moving beyond those to distributed representations. So soft clustering representations are distributed representations. So LDA gives you a distributed representation, LSA gives you a distributed representation, real HMM clustering does too. And really, neural word embeddings are in the same space, that you're taking the vector space semantics where you're representing each word as a vector over a bunch of dimensions, maybe approximately 100 dimensions. But it has the advantage that you can then get prediction tools built on top of that in ways that we'll talk about. So here's kind of project a picture of what you get from neural word embeddings. Unfortunately, you can't see anything in this one, but if we blow it up a little, we can start to see words. And if we pick some piece of the space and blow it up more, we can see here the countries, and if we move to a different part of the space, we can see here some of the verbs. So what this is doing is taking a 100-dimensional space and is then projecting it down to 2 dimensions by PCA. I mean, they're fun to look at, these word projections. They're also potentially quite misleading because you're losing so many of the dimensions of the space. Okay. So neural networks are in the same, neural embeddings are in the same general space of being vector space representations of word similarity. And they're not night and day different if you're just considering them as a vector space representation. The reasons why you might be especially interested in neural embeddings is because they have this special property that we can build them into bigger systems, which we'll do in our deep learning models, where we can then add supervision for one or more tasks. And so, for example, many things like sentiment or antonyms aren't naturally captured if you just build vector space models. But we can add those into our models by employing supervision. And it also gives a way of building representations for larger linguistic units, which is what we'll talk about in part 2, how to extend things up to phrase representations in the vector space. Okay, so the final piece of what I'm going to then talk about is, well, how do we actually concretely make these unsupervised word vector representations? And so there are various ways of doing it that are being explored. The one that I'm going to talk about is the one that Renan Collier and colleagues have used, which uses a very simple idea that works very effectively. And the idea of this one is, for any word that we want to learn its representation, which will normally be all words, we have the word in a particular context. So here it is, word on in the context of cat chills on a mat. Then what we're going to do is we're going to build a negative example corresponding to the true example by substituting the word of interest in the middle of the context. So this idea is similar to the implicit negative evidence, contrasted estimation that other people such as Smith